Good afternoon. My name is Sahil Gupta. I am a graduate student in Rochester Institute of Technology. Today I am going to present our demo paper, Simple Deep Packet Inspection with P4. Network security is an essential part of modern internet. Network security elements like intrusion detection systems and firewall analyze network traffic to detect malicious activity. They perform important security functions like monitoring system calls, application layer protocol event detection, inspect packet content, detection of reconnaissance attack, access control policy violation, distributed denial of service attack, data leakage, malware detection, and so on. Deep packet inspection is one of the core functionality of these security elements in order to provide security in cyberspace. In this process, the content of the packet are analyzed. This helps in maintaining essential services like lawful interception of traffic, copyright enforcement, surveillance, filtering of traffic, collection of useful statistics, and maintaining of quality of services. During our study, we find that there are three types of pattern matching cases used in DPI process of popular network IDSs like Zeek and SNOT. These are simple basic string matching, regular expression matching, and Perl-compatible regular expression matching. The computational complexity and memory requirement vary for different cases. In past, people have offloaded different kind of network and network security function from dedicated middle box hardware to data plane. Some examples are port scan attack detector, DDoS attack detector, firewall, network function, load balancer, network proxy, and flow-based Trojan detectors. But none of them has used DPI process to accomplish any of the middle box security function. The data plane router technologies are themselves not inherently designed for DPI functionality. For our work, we have chosen a basic string matching DPI case. This covers an important service of filtering based on domain name of or URL information. This information is usually seen in TLS client hello, DNS request, and HTTP GET request packet of network traffic. Government and ISPs uses this DPI technique to prevent access to website, hosting some illegal content like child pornography or involving in selling of illegal drugs. The major motivation behind this work was to test the feasibility of data DPI technique in data plane router itself, and to measure the possible saving of bandwidth and compute power in DPI execution. We also want to test the accuracy of the pattern detection in the traffic passed from data plane. But we have some challenges in its execution. The field in application layer protocol headers are either optional or present in different order or has a variable length. This makes starting and ending position of domain name in network packets highly variable. This is a crucial data point required in order to write a P4 parser program. So our research question is, in spite of these above challenges, is it possible to perform a simple deep packet inspection in data plane and reliably detect URL in traffic in all practical significant cases and for multiple important protocols using only standard P4 compliant switches? To answer this question, we conduct a short survey using three most popular browsers. Those are Google Chrome, Microsoft Edge, and Mozilla Firefox. And we use different operating systems, that is Microsoft Windows 10 and Ubuntu 18.04 LTS, to access the Alexa top 100 websites. These 100 sites generate several thousands of DLS and TNS connections to CDN subdomains and email servers. In this survey, we collected the relevant PCAP having TLS and DNS packets. From TLS client hello and DNS request packet, we observed via Wireshark the value of variable X, Y, and Z. The X is the length of the packet from starting byte up to TCP header in TLS packet, and for DNS case up to UDP header. Y is the length of packet from TCP endpoint to domain name starting position, and Z is the length of the domain name itself. We observe the variation is X is predictable and quantized. The variation is due to the protocol version like IPv4 or IPv6, and such variations can be tackled at a parsing stage without much trouble. Quite interestingly, we found no variation in Y, and the variation is that is limited from 10 bytes to 24 bytes in length. These variations can be tackled by parsing maximum length URL and filling the missing bytes with a don't care condition in the TCAM match action table. After observing a different variable distribution in different protocols for different websites, we also want to develop a data plane program to illustrate the point. We created network topology using Mininet emulator to host H1 and H2 runs client and server programs. The traffic generated from H1 passes through P4 BMV2 virtual switch and it reached host H2. The traffic passed through switch get parsed and application header layer bytes are extracted. The extracted bytes from application layer in packet parsing phase get matched in ingress pipeline of switch to detect the concerned patterns. We use TCAM memory match action table for our purpose. Patterns to be detected are installed from control plane in form of low-level data plane rules. We measure switch delay and web response time for each protocol with varying pattern to be detected. To compute results in automated fashion from PCAP, which is extracted from Mininet virtual network interface, we created a SCAPI-based Python script. Similarly, low-level data plane TCAM match action rules are also generated in automated fashion via Python script, which take patterns to be detected as an input and output low-level data plane rules. In conclusion, we observe a basic case of string matching is viable via P4 compliant data plane switches. In future, we would like to build solution in P4 compliant real switches rather than using a BMV2 software data plane. It would be interesting to see the distribution pattern of starting and ending position of domain name in packets for more number of websites to get more accurate stats on starting and ending positions. We would also like to develop a technique to inspect complete TCP and UDP payload, eliminating the issue of variable positioning of domain name in network packets. A separate video of our experiment for our demonstration purposes can be seen in our virtual booth. For any further question, please feel free to reach me or my team. Thanks for your interest in our work and hope you enjoy the remaining ICNP session.